Okay, so imagine that you have a cake, because who doesn't like cake? And you cut the cake in half and give half of it to one person. Then how much is remaining? One half, right? And then you decide to cut that in half and you give a quarter of the cake to somebody else. And how much is then remaining? A quarter. And then you take that quarter and you cut it in half. And how big is that piece? An eighth. And so then you have 1/8 left over. And so you take that 1/8, you cut it in half, and you give it to somebody else. And they get 1/16. Okay? This pen is not working well. And so forth and so forth. So what if we want to do this in like an infinite amount of times? If you keep cutting the cake in half, how many people can you feed? When have you distributed the entire cake? So if we think of infinity is not a number, its number is getting larger. If we think, are we always going to be able to cut the previous term in half? Yes. It doesn't like if we, even when we get to all the way down the road, right? You can still cut that number in half and that next number in half. So will you actually get to the end of the cake? Well, only if you do it an infinite amount of times will you then get. But infinite is not necessarily a number. It's doing it forever. So if you do this forever and ever and ever, then eventually you'll get to the entire cake. So it's kind of an abstract concept. We talk about it a lot in calculus. And usually this used to be a calculus kind of concept. We've introduced it into Math 20. And we used to prove it with calculus. But we're going to kind of prove it, but not really. Because you really need calculus to prove it. But so our geometric formula, term 1 is 1/2. Common ratio is 1/2. Power of n minus 1. Divided by 1/2 minus 1. So what we can do here is we can actually use some exponent laws. So first 1/2 minus 1 is -1/2. Here I'm going to distribute, these can reduce out. We have 1/2 divided by 1/2, right? They cancel each other out, but there's a negative, so we're just going to put that in front. Or I can distribute then a negative to each one, so it becomes a +1, put that in front, and this becomes -1/2 to the power of n. And so what happens is as this gets larger and larger and approaches infinity, then 1/2 to the power of that would approach 0. Okay? And you don't need to prove that in any way, but it's going to, if you do it an infinite amount of times, if you had 1/2 to the power of infinity, that's going to approach 0, what we say. Okay, it's essentially going to become 0. Why? Because 1 to the power of anything is 1, and 2 to the power of the largest number ever is going to be so big. So 1 divided by the enormous number is basically approaching 0. So grab your calculators for a second, and you'll see that your calculators are very limited. So when we type in, so let's type in different values of n. So this is how much of the cake you've given away, right? If you've done n slices. So 1 minus bracket 1/2. Let's put a large number in here, to the power of a large number. Give me a large number. 256? We said 156. 256. See, already that's going to be so big that your calculator is going to say that equals 1. Right? Even if I did, say, 10, you'll notice, okay, the sum is getting close to 1, but your calculator is going to be limited. It gets to a point where it just says, okay, that's so small that it is 0. Okay, and that's that happens with infinity. So if I try like, I don't know, 50, is that, like, your calculator is going to be limited. 1/2 to the power of 50 is really large, or really small actually. 2 to the power of 50 is really large. So 1 over enormous number is essentially going to be 0. And so what happens is the formula changes, and we are not going to prove the formula, but this formula here, we're not going to prove the formula, but it's going to essentially become 0, and so then it just equals 1 full cake. After an infinite amount of times, you've cut up and you've given this whole cake. So we're going to look at infinite series today. So infinite series are series that don't end, that go on for infinity, that have dot, dot, dot after it, and there's no last term. Okay, that's going to be an infinite series. And there's two types of infinite series for geometric. Okay, I'm just going to grab a couple of things. So when it's geometric, if it's an infinite geometric sequence, it can either be convergent or divergent. Okay, so an infinite series is one, oh, that's not a pen. So if I had 2, 4, 6, oh, that's not geometric. 8, 16, dot, 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 right? That's going to be an infinite series. Actually, if it's a series, what should I have instead of commas? Plus signs. Miss Jones. Okay, plus signs. That would be an infinite series. So we want to add up the terms, and there's no final term, okay? So convergent, if something converges, it actually approaches something if it converges. So it's going to approach some number. Oopsie. That's not where you sit, Sky. You should go back to your seat. You're Jackson. Sky. Sky. Yeah. Why don't you move? Drawing too much attention to yourself. Okay, divergent. If it diverges, it does not approach some number. So usually we say that infinite sum, if it diverges, approaches positive or negative affinity. So it's just going to keep getting larger. So how do we know if a series is going to actually converge to some number? Like the example of the cake. The cake actually approached 1. And when we add up those terms, we have full cake, and when we cut it in half, plus quarter, plus eighth, when we do that infinite amount of times, it gives you 1. As long as we do it infinite, it actually approaches 1, approaches some number. So this guy, what was his common ratio? 1/2, right? So let me give you an example of a divergent series. If we look down below, here are two examples of divergent series. And divergent series, what do you notice about the numbers in general? Let's look at the very first example. What's your common ratio here? 2. So the numbers are getting larger and larger and larger. And so the infinite sum is just going to keep getting larger and larger. It's going to approach positive infinity in that case. Now, this one's very interesting because the sum, it doesn't approach some number. It keeps going back and forth between positive and negative values. So what's the common ratio here? -2. So for example, the first sum is -4. The sum of the first two terms is +4. The sum of the first three terms would be +4 minus 16, -12. So then the sum of the four terms, right? It keeps going back to these positive and negative numbers. It doesn't actually approach, if we keep doing this an infinite amount of times, it's not going to approach some number. It's all over the place, these sums. And so notice that these R values this one is either greater than 1 or less than 1. So the common ratio is really important. It tells us if it's going to actually converge on something or if it's going to diverge. So a divergent series occurs when your common ratio is greater than 1 or less than -1. Now we're not going to talk about if a series has a common ratio of 1. They're actually pretty boring series, or a common ratio of -1, especially 1. Like a common ratio of 1, it's pretty boring. So if I want to sum three terms together, it would be 5 times 3. Your first term times the number of your n value, because it's just the same thing over and over. Okay? So convergent, that's where it gets interesting. Okay? A convergent series occurs when your common ratio is between -1 and 1. So that was like our example of 1/2, or if our common ratio was -1/2. It's very, very interesting. Notice that our numbers are going to keep getting smaller and smaller and smaller. Like look at 4, 2, 1, 1/2, 1/4, right? They're getting so small that as we do this to infinity, the infinite terms are like basically nothing. They keep getting smaller. That we're going to have an infinite sum that approaches something. What's your common ratio on this first one here? 1/2. Does anyone know the common ratio for the second? -2/3. So the signs are switching, so negative. The numerators, we're multiplying the numerator by 2, and we're multiplying the denominator by 3, so 2/3. Okay, so notice the numerator is times 2, the denominator was times 3, and then it's switching signs, so -2/3. So that's where that fraction comes in. Okay, so notice that these values, these actual values, your actual terms, are actually getting, ignoring the sign, they're getting smaller and smaller and smaller. And so that's why they actually approach something. And so that's where this formula on your formula sheet, that's S infinite. So only if it's convergent can we find the infinite sum, because it actually will approach some number. Only if convergent we can find the infinite sum. That's awful English. If it is convergent, then we can find I don't know. Oh yeah, I should take away that. That's awful. Sorry. Good thing it's Friday. And so only in that case, only if our R, it's a geometric series and R is between -1 and 1, can we use the formula that's on your formula sheet. That's term 1 divided by 1 minus R. And it has to do with the formula. We're not going to prove it. We don't have to prove it. You can prove it in calculus. But it has to do with basically taking one of your geometric series formulas and doing some calculus, and then we get this formula. Okay? So that's the only time you can use that formula. You try to use that formula, sure, it'll give you an answer, but your answer is wrong if you try to use it for a divergent, because the sum is actually going to be positive or negative infinity, or it's just not approaching anything. Okay? So let's classify each one of these as either convergent or divergent. So in order to tell that, we need to figure out the common ratio. So our common ratio in the first one is 3. So convergent or divergent? Divergent. So numbers that are between -1 and 1 are like fractions, right? Or decimals that are small. Next guy, what's the common ratio? Number term 2 divided by term 1. What? Is 16 half of 64? 1/4. 1/4. Yeah. 1/4. So where does that fall? Is that divergent or convergent? Convergent. So we can actually find the infinite sum if we wanted to for that series. Next guy, what's your common ratio? Term 2 divided by term 1. What does that reduce to? -1/2. Convergent or divergent? Convergent. So the infinite sum exists. Okay, so this is our formula. It's on the formula sheet. It only works for geometric series, and I'm pretty sure on your formula sheet it even shows R has to be less than 1 and greater than negative 1. I think that's even on there. So like, it lays it out for you right there on your formula sheet, that your R value has to be between negative 1 and 1 for you to use that formula. There is no answer if it's not geometric and convergent. Okay, so we're going to find the sum of each one of these. We have to make sure it's convergent. What's the common ratio here? So instead of going 1/6, like, what are you multiplying your numerators by? 1. What are you multiplying your denominators by? 4. So it'd be 1/4. So that is convergent or divergent? It's convergent. So because it's convergent, then we can use this formula, the infinite sum formula, which is term 1 divided by 1 minus r. What's term 1? 1/4 divided by 1 minus, common ratio is 1/4. So you have to be very careful when you enter that in your calculator. I'm going to put brackets around my numerator and around my denominator. So bracket 1/4 divided by bracket 1 minus 1/4. I don't have to worry about putting the brackets around the 1/4 there at the bottom, because with BEDMAS, your calculator is going to do BEDMAS, right? So it's going to divide that and then subtract. What does that equal? A pointer repeating. Math, enter, enter. 1/3. Should probably know that one anyways. So that's the infinite sum. That if we sum these terms to infinity, they're going to add to 1/3. Keep doing that for the rest of our life. Okay. So next guy, what's your common ratio? Term 2 divided by term 1. 1/3. So therefore, convergent. And only if it's convergent can we use the infinite formula of term 1 divided by, it's the easiest formula. I love it. So simple. So what's our first term? 3 divided by 1 minus 1/3. So make sure to wrap your denominator in brackets when you enter that. And we get, so because it's a terminating decimal, it's fine if you answer as a decimal. If it's a repeating decimal, then you need to change it to a fraction, right? So 9/2 or 4.5 is perfectly acceptable because that's a terminating decimal, right? Alrighty, so I'm going to add a couple questions. So this is where there's 3 questions I'm going to add. Sorry, I ran out of room. I didn't print it actually. So I'll make this a little maybe larger for you. See if you can do it all. Oh, I wish there was something in between 150. Oh, I'm not recording. Just so I remember. Thanks. Okay, term 3 was 16x squared. So you might need your calculator for this. So 16 times 2/9 squared. So enter that in, figure out what that equals. Two over 9 should be in brackets and then squared. When you're squaring a fraction, has to be in brackets. And to avoid a decimal, we push math, enter, enter. 64/81. See, we can actually see that our common ratio is 8/9. So we're multiplying numerator by 8, denominator by 9. Okay, in the term 4, there's a few ways we can get it out. You can figure out Well, each time we were multiplying by 4x squared, the next term would have been 64x cubed. So that's one way, figure it out. Or use your common ratio. You can see your common ratio is 8 over 9. The first term is 1. The second term is 8 over 9. The third is 64 over 81. So multiply that again by 8 over 9. You have two options. Okay? If you want to use 64x cubed, you can do that too. Oops. So it's going to be large. 64 times 8 and 81 times 9. We should have 512 over 729. There's the first four terms. Okay. Example number 4, it says write 0.89 repeating as a fraction using the infinite sum formula. So back in grade 10, you might have learned that if I wanted to take a repeating decimal in my graphing calculator and make it a fraction, I just type a whole bunch of them and then go math, enter, enter, right? And then I'll make a beautiful fraction for you, 89 over 99. You'd have to do a whole bunch, and then it'll convert it. It assumes it's repeating forever, and then it'll convert it to a fraction. We can also use our infinite sum formula because it actually is a geometric series. We can make it into a geometric series. And I'm going to show you how. Okay, your first term is 0.89. We're going to separate each of the repeats. Okay, so there's the first two decimal places. Okay, plus, now if I want the next 89, that's the third and fourth decimal place. We already represented the 89 originally, and so this next one would be 0.0089 for those two. Are you with me? Okay, one second. Think of it this way before I write it out this way. Okay, this is 0.89. This guy here is 0.0089. Right, if we all add these all up together, 0.000089 for those two. The next term would be 0.000089. We add these all together, then we get the 0.89 repeating if we keep going for infinity. Okay, do you see how we're doing that? It's lined up that way maybe a little bit better. And so that forms a geometric sequence. It forms a geometric series actually. 0.89 plus 0.000089 and so forth. Okay, so we're going to put that into the geometric formula, the actual infinite sum formula. Because what is our common ratio? Now you can get term 2 divided by term 1. That's one way you can get it. Or, well, what do you get when you divide those two? 1 over 100, or 0.01, because we're adding two decimal places every time, right? 0.01, that's our common ratio. Is that between -1 and 1? Yes, so therefore it is convergent. We can find the infinite sum. Our first term would be 0.89. So our infinite sum would be term 1 divided by 1 minus our R value. Okay. What is 1 minus 0.01? Negative or positive? No, you're added. Yeah, you're 0.99. That's okay. Went the other way. Yeah. 0.99. So now I want to get rid of the decimal. We can do that by multiplying top and bottom by 100. Gives you 89 over, no? 99. We're just moving the decimal place 2 to the right. And there's our infinite sum. Is that not what we got on our calculator? Sure is. Okay. So we can use the infinite sum if we have a repeating decimal to actually make it into a fraction. Very exciting. So, is 0.9 repeating equal to 1? Do you have an opinion on this? Let's see if 0.9 repeating actually is 1. Alrighty. So, if we had 0.9 repeating, or 0.999999, keep going to infinity, is that the same thing as 1? Let's find out. So we can make this into a geometric series. Each one of the repeats would be its own term. So 0.9 plus, what would be the second term? 0.09 plus, we're doing 1 9 at a time. This one, because the other one had two things that were repeating, this one just has one number. So it's one thing at a time. So what's the next term? 009, good, and so forth. Term 1 is 0.9. What would be the common ratio? What's term 2 divided by term 1 equal to? 0.1, 1/10. 1/10, which is invergent. So let's find the infinite sum. Term 1, 0.9 divided by 1 minus our common ratio of 0.1. Thrilling stuff. 0.9 divided by 0.9. Anything divided by itself is 1. So 0.9 repeating as a fraction is 1 over 1. Exciting. Isn't that cool? So it actually is. Okay, so people tell you 0.9 repeating is not the same thing as 1. It actually is. I know. It's kind of weird to think that, but it is. 0.9 repeating is 1. There's different ways to prove that. You might have seen other ways before, but that's very exciting. So we're done. No, are we? Yeah, we're done, right? Yeah. This is it. You wouldn't know because you don't have it in front of you. Okay, so I'm going to stop the video.